There are many models of classical computation. Last time we discussed a few of them, and you shouted out a few of these models. And what I'd like to do is to illustrate a wide variety of models, some of which you might find unexpected. So for example, one model of mechanisms by which you can build computers is actually mechanical. Can anybody tell me of a mechanical computer you've met recently or know of in history? Yes, please. Abacus, beautiful.
I think there's one in Stata, right?
Yes, there is. There's like a differential analyzer that uses it's not the differential analyzer, but it's a machine that does some kind of addition by having a ball rolling down. Beautiful. Yes, please.
The old Curta calculators?
The old?
The rotary Curta type calculators?
Yes, the old rotary Curta type calculators. But there's more than that. The thermostats on the walls, at least at MIT, are driven by pneumatic pressure, and they actuate a little switch. So they're a little kind of computer that controls temperature, but it's an analog computer. So mechanical computers do not need to be digital like the one in Stata. They do not have to be abacuses that do kind of integer arithmetic. They can come in all kinds of shapes and forms. And the one that's perhaps the most famous in history is Babbage's difference engine. And it had this feature that if he had been able to finish it, it would have become or could have become a universal computer in the sense of universality, as I hope you'll see. So here's another one. We saw this one last time. We can have electrical circuits, which are ways of building a universal classical computer. We can also have optical computers that are made out of information carriers that are photons and not electrons. Here's another one, biological. So in many ways, you and I are walking, talking computers in some kind of sense. And this idea of biology and biological systems as computers is currently going through a renaissance because of the notions of neural networks and deep learning and these kinds of networks of neurons that act as computation. I also want to make a distinction between these models and some conceptual models. These are models by which you might realize computation, and these are the conceptual models which you might want to realize. One of them was described last time in some general notions, which is the Turing machine. And for those of you who don't know what a Turing machine, since that wasn't described explicitly last time, it is a machine that has a head and a tape. And the tape has slots on it, which may have ones and zeros. And it is something which has an extent to left and right, which goes off in principle to infinity. And the tape is a kind of memory. And the thing which is ostensibly doing the computation is a head that can read and write to this tape. But the only thing inside this head is a finite state machine. So there are different states, and there are transitions between the states, which happen depending on what is read at what time and the previous state that it used to exist in. And Turing machines like this come in many different flavors. So for example, there are probabilistic Turing machines, and there are universal Turing machines. So given a certain kind of structure of a finite state machine here, you find that this Turing machine then is capable of simulating any other Turing machine. And then one of my favorites that's not widely known about today is called Minsky machines. Marvin Minsky, a professor who pioneered much of this area, passed away recently, asked this beautiful question about the minimum size of the head that you need to build a Turing machine to accomplish different tasks, for example, being a universal Turing machine. And so that's the topic of Minsky machines, which we won't have time to go into here. Here's another model, cellular automata. Today, the buzzword is neural networks. Maybe 30 years ago, one of the buzzwords was cellular automata. And here, the model of computation is a world which is a grid in 2 dimensions, in n dimensions, where the point is that you have some kind of state in a local cell of this grid, and it undergoes transitions based on the state of its neighbors. And you may have a local Cartesian neighborhood, you may have super Cartesian, but depending on what you're surrounded by, you change your state. You change yourself to becoming empty or filled or a different color and so forth. And these rules of patterns and pattern changes can give rise to computation and how we can understand, for example, Conway's rule of Conway's game, which gives rise to something which people interpret as life. Okay. There's the von Neumann architecture. I called it an architecture. It is, again, a conceptual model of computation. And here the idea is to split memory from something which does arithmetic. So we have an arithmetic logic unit, for example, maybe some registers. Memory reads out from the reads out data and feeds it into this ALU, and then the ALU feeds data back into the memory. And this is, by and large, the model that's used by all processors today, including the ones on all of your phones. So here's another model of computation. How many folks have ever encountered DNA-based computation? It's a rather wild concept. A few of you have. So this is the idea that maybe you have strands of bases, A, G, C, T. And then A and T, adenosine and T, which I can't remember right now, associate each other. And this is called ligation. And then G and C also ligate together. And therefore, when you have 2 different strands of DNA, they will pattern match other strands in the right locations, which match the sequence of bases to produce base pair ligations. And this has been shown to allow a kind of computation, christened as DNA computation. And so these biological operations include primitives that are different from the kind of gates that we might think of for electrical and optical, such as melting. So this is melting of strands, separating them into different parts, appending, adding 2 strands and kind of connecting them together at the ends, cutting, and doing things like restriction flip enzyme rip flips, which are used to insert pieces of the genome in different places, and then amplifying for measurement using polymerase chain reaction tools. So that if you have a beaker, for example, with just 1 DNA strand, with PCR, you can amplify the number of DNA strands there so you can detect the existence of a certain sequence of DNA. High school students are now doing this with little kits, and you can even use a swab to pull DNA out of your mouth. And so it's really neat that you can think of using such tools to do computation. And I want you to be open to such kinds of models of computation, especially today, because it is in your generation that we are now starting to reconsider what it means to do computation. In many ways, we are at the end of the road of silicon today. We cannot rely on Moore's law much longer to provide an increasing scaling that's exponential of capability and size and power and weight to build our computers. We need to look at different physical mechanisms to build computation. And that's why all of these different approaches where you represent information in different ways is so appealing to think about, because maybe the next thing beyond silicon could be something different, very different, that utilizes these ideas. And maybe what we might discover is that it's already happening all around us or within us if we only know how to think about it in the right way. So although this class is about quantum computation ostensibly, what I want you to also think about as we go through this journey of quantum computation is how we're also thinking about a broader question of what is the physics of computation? How do you think of physical mechanisms as doing computation? And how do you think you might be able to exploit physical mechanisms and biological mechanisms that exist to realize the computations that you want to achieve? So let's keep on going through this journey. And I hope you'll find some things that are unexpected and exciting. You know, there are lots of interesting opportunities that arise. Today, we have the excitement of CRISPR-Cas9, which changes the opportunities of what's available for DNA computing because it allows you to snip out very specific locations and patterns of DNA. Does this change the complexity of what you can achieve with DNA computing? I don't know. But lots of things are changing in this avenue. And people don't normally think about it with the glasses of computation on. And I encourage you to do exactly that.